All right, so this lesson is about alkenes. So first, we're going to learn how to name alkenes. And to name alkenes, you're going to need something called cis versus trans isomerism. We're going to talk about that next. And later, we're going to do reactions with alkenes. So what type of reaction do these guys undergo? And finally, Markovnikov's rule, which is needed in order to learn reactions of alkenes. So let's start with some definitions. Okay, so when you have a single bond, you would have alkanes. And alkanes are considered to be saturated with hydrogen because you can't add any more hydrogens. All of the bonds have been used. And here's the general formula, CnH2n plus 2. That was from last time. But if you have multiple bonds, you can have double or triple. So if you have a double bond, it's called alkene with E and E instead of A and E. And it is unsaturated. Okay, it's unsaturated because you can still add more hydrogens. How? If you break that double bond, then both carbons would now have room for one more bond, and those would be hydrogens, so that would be unsaturated. The formula would be CnH2n, so there's twice the amount of hydrogen compared to carbon. And triple bonds are called alkynes, and they are also unsaturated because just like alkenes, you can break that triple bond, then you will have extra bonds available for hydrogen. So you can still add more hydrogen. So this is unsaturated, and the formula would be CnH2n minus 2. If you compare their formulas, you can see that with double, you lose 2 hydrogens from the alkanes. And with the triple, you lose 2 hydrogens from the alkene. All right, and this makes sense because as you have more bonds, the carbons having more bonds with each other, you're able to make less bonds with hydrogen. Okay, so that's why you see a pattern like that. And finally, aliphatic hydrocarbons. So basically, that's a compound that has a structure that is a straight or branched chain or rings. So basically everything that we've learned and will learn will be aliphatic, okay? So how would you name alkenes? So the rules for naming alkenes have some clear differences than alkanes, so please listen carefully. The first thing is you have to identify the parent or the ring that is considered to be the parent, okay? But that parent chain must contain the double bond. You can't just avoid the double bond and call this the parent. If it has a double bond, it better be in the parent, okay? And the name will end with E and E instead of A and E. So that's the first rule. Second is that if you have more than one double bond, well, then you have to add a suffix at the end to denote the number of double bonds. If you have 2 double bonds, for example, it would be diene. Okay, if you have 3, that would be triene, and so on. And next, you have to number the carbons in the parent so that the first carbon the first carbon in the double bond must be as small as possible. So forget about satisfying the lowest set of numbers. Okay, you have a new priority now. You want to make sure that the double bond has the smallest possible number. All right, forget the rest. Care about the double bond. When the double bond has the smallest number, then you worry about the lowest set of numbers. Okay, so we added a brand new level of priority here. So number 1 priority, double bonds must have the lowest number. If you have a tie, cool, you move on to the next one, the lowest set of numbers. If that's a tie, you move on to the next one, alphabetical order, okay? And you need to tell me where is that double bond. So you write the number before the suffix, and I'll show you what I mean. Lastly, you name any substituent branches. The same rule for alkanes. This is quite intuitive. That's not different, all right? All right, so let's look at some examples to show you what I mean. So here is example 1. You have 2 questions here. The one on top, if you count them, you have 5 carbons. And the double bond is between the first and the second carbon. You can count this from the left or from the right. Now, obviously, I just said you had to minimize the number on the double bond. So, of course, you will count from the left so that the double bond will be on carbon 1 instead of carbon 4. So you take the first set of numbers, and then you can now go ahead and name this 5 for penta, but you can't have A and E anymore, so it's E and E. Pent 1-ene. You need the 1. If you don't have the 1, you just have pentene. Well, you're not telling me where your double bond is. Okay, the E and E tells you that there is a double bond. The 1 tells you the double bond is on carbon 1. The 1 is necessary because it could be on carbon 2. Okay, so please make sure you write the 1. So it's pent 1-ene. Does that make sense? All right, so the next one, you have a ring. Okay, so a ring, you have 4 carbons in the ring, so that's a butene because of the E and E. And because you're in the ring, you are cyclobutene. Does that make sense? Now, how come there's no 1 in here? Can anyone answer that question? Why isn't it cyclobute-1-ene?
Because whenever you can choose whatever to be the 1, where it depends on where double bond is.
Exactly. Okay. Wherever the double bond is, that would be carbon 1. So the double bond has no choice but to be on carbon 1. So when you have no choice, you don't write the 1. It must be this way. So it's cyclobutene, and this is different from pentene. Pentene, you have a choice. It could be between 1 and 2 or 2 and 3. Okay, you good? Okay, what about example 2? Now, the one on top, you now have a branch. You can count the carbons. Okay, 5 carbons in the longest chain, and you can count from the left or the right. And obviously, one is better than the other. Which one is better, from the left or from the right?
From the right.
From the right.
Yes, from the right. If you count from the right, the double bond is on the first carbon, which is exactly what you want. You want that to be as small as possible. But if you count from the left, the double bond end up on carbon 4. That's bad. So you count from the right. The parent will be pent-1-ene again. Okay, that's the longest chain. We name it pent-1-ene. The branch will be 4-methyl. You put this together, it is 4-methyl pent-1-ene. All right, so notice that this is very similar to naming alkanes. The only difference is you have to account for the double bond. Now, it gets a little bit harder if you have more than one double bond. The next example, you have 2 double bonds. And in this case, it doesn't really matter from what direction you number these because you're going to end up with 1, 4 in both directions. So I'm just going to arbitrarily choose the first one. All right, so what would be the name? Anyone want to venture a guess? No takers?
1,4-dipentane. No way. Pent 1,4.
Uh-huh.
And something.
Something like that?
Yeah.
Yeah, you're on the right track. You just needed to finish that sentence. You have penta-1,4-diene. Okay, so many things to note in this name. First of all, diene. You need the di because you have 2 double bonds. That denotes how many double bonds, so make sure you put the di. 1,4, you got to tell me where you find those double bonds, so on carbon 1 and carbon 4. Okay, that makes sense. What about that A I highlighted in red? If you compare before, you have pent-1-ene. So how come now it's penta-1,4-diene? You must have the A. Spelling matters. So how would you remember to put the A, you might ask? Well, the pattern that I've noticed is that you cannot have 2 consonants together and you cannot have 2 vowels together. A consonant must be followed by a vowel, and that must be followed by another consonant. Okay, if you just bring your attention to the first name, 4-methylpent-1-ene. Imagine that you don't have the 1 right there. You would have pentene, right? That sounds nice. That sounds natural. It rolls off the tongue very nicely, pentene. I think there's a shampoo called Pentene, but that sounds good. T followed by the E sounds very natural in English, so it's pent-1-ene, no problem. But when you go to the next one, if you just delete the A and you just pronounce it pent-diene, that kind of sounds awkward without something in the middle to connect the two consonants together. So instead we add a vowel A, so pentadiene sounds a lot better. All right. So whenever you have two consonants, you must add a vowel, and that vowel is, I think, always A. So penta 1,4 diene. Does that make sense? That's how you know you have an A there. If you don't, pent-diene, you have two consonants, sounds weird. Okay, that's not a choice. You have to have the A. Does that make sense? Okay, cool. All right, so this brings us to isomerism, specifically cis versus trans. Consider alkanes, with the thing we learned last time. It doesn't really matter which orientation you look at the alkane from, because you can rotate that bond. Now imagine one of the H's on that alkane becomes, let's say, a chlorine. So you have chloroethane instead. Does it really matter on which H do you substitute for the chloro? Does it? Well, the answer is no. Why not? Because you can just rotate it. If you decide to put the chloro on the H that goes into the page, well, guess what? Just rotate it until it comes out. You have the chloro in another location. And then rotate it again, it becomes on the bottom again. So it doesn't matter at all where you put the chloro, because you can just rotate everything and it will just be the same structure. Okay, so that's why alkanes, they do not exhibit any isomerism, because they can just rotate. But double bonds cannot rotate. Okay, if you have a double bond, it is too rigid. If you rotate it, you break the bond. So now it does matter where you put the chloro. If they happen to be on opposite sides of that double bond, well, those chloros will never be on the same side. You can't just rotate it so that they are all pointing in the same direction. They're stuck there. And if they're already on the same side, there's no way to separate them. They're stuck together. Hence, you have cis versus trans isomerism. All right, so for alkenes, because of the rigid double bond, you can't rotate that. So whatever is on the same side or on opposite sides are stuck that way. So you must distinguish between the two types of isomers in the name. All right, if they're on the same side of the double bond, we call it cis. If they're on opposite sides, it is trans. Okay, you may have heard of trans fat when you buy food. I always read the label on the food to see what I'm eating. And if I see trans fat and I don't crave it that much, I'll put that down, because I know trans fat is very terrible for health, especially for your heart. So trans fat simply means the two hydrogens on the fatty acid points in the opposite direction. If you took biology, you know exactly what that means. Now, this is exactly what we're talking about. In this case, you can see that the two, methyls are pointed in opposite directions. That will be a trans. But for cis, the two methyls are in the same direction. Okay, I call them methyls. They're not actually methyls, but you know what I mean. So this is called stereoisomers. Okay, within isomers, there are subdivisions. So first of all, an isomer, just to review, is just different structure but same atoms. You just take those atoms, you bond them differently. Okay? It's like you assemble Lego, you can assemble them differently, but the same Lego pieces. A stereoisomer, however, you have the same structure. It's just that the structure looks different in space. They are arranged differently with this different orientation. It's like you have one arm pointing up. Well, now I move the arm to point down, you have a different isomer. Okay? So those are stereoisomer, and cis and trans, they are stereoisomers. So do we have any questions regarding cis and trans, first of all? All right, so do you guys have any issues recognizing cis from trans? Just look across the double bond. Imagine that the double bond is a river. If two things are on the same side of the river, well, that's cis. And if they're across from each other on the opposite sides of the river, that would be trans. Okay? So how would we name cis and trans using IUPAC nomenclature? Well, you can't simply just write cis and trans. It's not that simple. It gets a lot more complicated than that. So IUPAC invented two new letters to represent cis and trans. So E and Z. E means that the high priority groups are on opposite sides. I'll explain what a high priority group is later. Okay, on opposite sides, you have E, whereas Z, the high priority groups are on the same side. So how do you remember which is which? Well, here's my way. E, it stands for enemies. Okay, enemies are on opposite sides. Z, well, the same side. The same side. So Z, the same side. Okay. E doesn't actually stand for enemies. It's a German word. I forget what word that is. So that's how you remember which is which. So, but what is on the same side? What is on opposite sides? Well, high priority groups. Okay, so what's a high priority group? A high priority group is a group with a higher atomic number. Okay, so now you have to compare. You have to compare between two different atoms on the same carbon to see which one has higher priority, which one gets special treatment. So to show you what I mean, let's name that thing in the example. Okay, first of all, you have to number the carbons. You can go from the left or the right. Obviously, going from the left is better because you would have a 2,4 for the double bond, whereas if you go from the right, you have a 3,5. So 2,4 is smaller, you go from the left. Okay, no problem there. The next thing you got to decide is, well, E or Z, are they on the same side or are they on the opposite side? Okay, well, first of all, that's the hepta-2,4-diene. That's the name of the parent. For the first one, the double bond on carbon 2, it is a 2Z. They're on the same side. What is on the same side? Well, consider carbon 2. Okay. What is being bonded to carbon 2? Well, carbon 3. So there's a double bond between carbon 2 and carbon 3. Okay. That's our river. And if you look at carbon 2, what else is bonded to that? Well, there's another carbon down. A carbon 1 is bonded to carbon 2. But is that it? Is there something else that you're not seeing? Yes, there's a hydrogen bonded to carbon 2. It's just that we don't show the hydrogens, but you have to know that they're there. All right, so on that carbon 2, you have two things that you have to compare. Carbon, well, carbon 1 specifically, and hydrogen. Does that make sense? Who has the higher priority? Well, it's got to be the carbon because you compare the atomic number. Carbon has higher atomic number, 6, compared to hydrogen's 1. So between the carbon and hydrogen, the carbon wins. All right, does that make sense? All right. Now you look at carbon 3. On carbon 3, you're connected to carbon 2 via a double bond. You're supposed to. That's why we're looking at you in the first place. But what else do you have? Well, you have carbon 4. You have a carbon attached to you. And another hydrogen which is not shown. Okay, hydrogens are implied. You then have to compare the two atoms connected to carbon 3. The hydrogen versus the carbon. Again, carbon wins because carbon has a higher atomic number. So we give the priority to you. So carbon defeats hydrogen again. So now you look at the two winners, the high priority groups. Look, they're on the same side of the double bond. And if you're the same side, you're Z. Did I make myself clear? Does that make sense?
Like by same side, do you mean like in the same place. Not the same place, but like in the same, like.
Okay, I know what you're trying to ask.
The same side thing.
Yeah, imagine that the double
okay,
bonds they're on the same side of that river. Does that make sense?
Okay, yeah, got it.
So if carbon 3 is connected to like a higher priority group, then it will be E.
Well, if the one that goes up is a higher priority, then yes, that would be E.
Okay. Yeah.
Now, actually, we have an E coming up right now. The carbon 4, that double bond there, that's an E double bond. Why? You have to consider carbon 4, okay? Imagine that the double bond between carbon 4 and 5 is a river. So carbon 4, you got two things on you. Actually, let's look at 5 first because 5 is simple. 5, you got two things on you. You got carbon 6 and you have an invisible hydrogen. Obviously, the carbon 6 wins because carbon is higher than hydrogen. Okay, no problem. But carbon 4, though. Carbon 4 has two carbons. Okay, the carbon 3 and the branch methyl. They're both carbons. And if they're both carbons, you have a tie, atomic number 6 versus 6. But you still have to make a decision. Which carbon is better? Okay, you still have to compare the two carbons. So you got to have a tiebreaker. If you tie with the immediate atom that you're bonded to, then the tiebreaker is, what is that atom bonded to? Okay, so look at carbon 3. That carbon 3 is bonded to another carbon. Carbon 2, right? So it's got a double bond with a carbon. Okay, that seems fancy. But that methyl group on the bottom is also a carbon, but that carbon is quite pathetic. It's bonded to 3 lowly hydrogens. So you suck. Carbon 3 is better. Okay, carbon 3 is the better carbon. So that wins. Do you follow the logic? If it's a tie, if it happens to be the same element, you compare to what that element is bonded to. Okay, so you go down the rabbit hole. If that's a tie, you go down to the next thing that's bonded to. So in this case, for carbon 4 and 5, the high priority groups are opposite sides, hence 4E. Okay, does that make sense, everybody?
Yeah.
Can we do another example?
Oh, for sure. There's more coming up. Let me just finish this example, all right? So once you determine that, that's a 4-methyl. Okay, that's the simple part. You put everything together. How would you do that? Well, the V and Z come first. So 2Z, 4E, you separate them with a comma and brackets. That tells you the isomers. On carbon 2, it's a Z isomer. On carbon 4, it's an E isomer. Then 4-methyl hepta-2,4-diene. Okay, that's the full name of this structure. That's how you would name cis versus trans isomers. Okay, I know that's a lot. I have more examples of this. Okay, to figure out which one is a higher priority can be confusing sometimes.
So for carbon 4, carbon 3 is the priority?
Yep, carbon 3 beats that methyl group on the bottom.
But how about carbon 5? Isn't it combined? Isn't it binded to that too?
Well, carbon 5 has carbon 6, right? In addition to that, carbon 5 also has an invisible hydrogen. So carbon 6 is clearly better than that hydrogen, so 6 wins. So that's why I put a check mark there. But for carbon 4, it's more difficult because it's bonded to 2 carbons. But not all carbons are equally good. It's kind of like real life. People are not equal. We want people to be equal, but realistically, people are not equal. Okay, for example, let's say I have 2 students in the class, right? Let's say 2 students break a beaker in my lab. Oh, I'm pissed. But who do I yell at? Do I yell at both? Well, if I'm an immoral person, if I'm biased, then I play favoritism. Some kids I like more than others, so I yell at the one I don't like. So how do I decide who do I like better? Well, it depends on your background, right? If your dad works for the government and I need the government to help me with something, well, I'm not yelling at your kid. I'm going to smile. It's all fine. I'll clean that for you. Are you okay? Are you hurt? If your dad is just, let's say another teacher like me, I mean, you can't do anything to me. So you know what? Clean up my beaker. You see what I mean? So if the two kids, I don't see any difference, I look at your parents. I don't actually do that. It's just an example. I look at your parent, an extension of your background. I was like, okay, you have a really, terrifying background. I don't want to mess with that. You don't have to mess with you. You see what I mean? That's how some people roll. And that's not something that we are advocating here. But basically, that's what's happening here with the atoms. You both have a carbon, okay, but like who's got the better carbon? Like, oh, you have another carbon behind you, so you have a better background. You have hydrogens. Yeah, hydrogens are weak. I'm going to go with the one with the carbon. You see how this works?
Yep.
Yeah, that's a dark example, but that gets the point across.
Is it always Z before E, or it depends on which number is smaller?
No. The smaller number comes first.
Okay.
2 before 4. All right, so let's look at more examples because this is confusing if you just look at one example. So for the first one, 5 carbons in total. And obviously you want to count from the left. The problem is it E or Z? Can somebody tell me?
E.
E, okay. It's E because the high priority groups, the carbons, are on opposite sides. So this one would be 2E, pent-2-ene. Does that make sense, guys? Okay, let me just label the winners here. This guy is better than the hydrogen. This guy is better than hydrogen. So they are on opposite sides of that double bond, hence E, okay? The one below that, however, this is the winner. Compare that to the hydrogen. Of course, that's the winner. That's the carbon. This carbon defeats its hydrogen. So they're on the same side. That would be Z. So that would be 2Z pent-2-ene. You see the difference in the structure here? One makes a cup. One looks like the Big Dipper. The other one is just a zigzag. The more confusing one is the last one. E or Z? It's still pent-2-ene, but is it E or Z?
E.
E? Why do you say E?
Because the methyl group is worse than the carbon 4.
Yes. Yeah, because we judge carbons now. The methyl group is worse than the other carbon because the other carbon has another carbon. All right, so, that one is easy. That one's the winner because carbon's better than hydrogen. But those two carbons, this one is the better carbon. So, and they're on opposite sides, so you have 2E, 3-methyl pent-2-ene. So is that clear, everybody? How to distinguish between the higher priority groups?
I have a question. So, for example, if we have, does it matter if we have like ethyl group there, like in the middle, like it's still?
So you're saying if that middle branch is an ethyl group, not a methyl, would that matter?
Yeah.
Okay, that's a very good question. If that becomes an ethyl group, so you would have basically 2 ethyl groups, then you wouldn't have EZ at all because they're exactly the same. If you're exactly the same, why are we distinguishing between the two? So we just omit the EZ for that situation.
Oh, okay.
Only if it's different. Okay, then you have to tell me which guy is on which side. If they're the same, who cares what is on what side? It's the same thing. Okay, makes sense?
Yeah, thank you.
All right. What if it's not carbon? Okay, so this one gives you chlorines instead. The first one, what would be the name of the first one? First one, E or Z? Z, same side. Well, how do we know that? It's Z, you're right. Chlorine versus carbon. Chlorine is bigger. Chlorine has an atomic number of 17. Carbon is just 6. So we go with the chlorine. On the other carbon, you have, again, chlorine versus carbon. So chlorine wins again. And they're on the same side, Z. So 2Z because the double bond is found on carbon 2. So this would be 2,3-dichloro-butene. Does that check out for everybody?
Yep.
Second example. You still have the 2 chlorines, except the 2 chlorines are now on opposite sides. So the high priority for the chlorines are now separate across from the double bond. So instead of instead of Z, you would have E. The only difference between this name and the one on top is the EZ. Okay, the structure remains the same. You have butene, you have 2 chlorines on carbon 2 and 3. The only difference is on which side of the double bond. So there is a difference between these 2 structures. All right, so the next one. How many carbons in total, first of all?
3.
3. All right. Only 3 carbons. So is there a cis trans for this one?
No.
No. Well, you can see that this chlorine is better than the carbon across. But on the other carbon, you have 2 chlorines. It's a tie. And they're not bonded to anything. So they're literally identical. So then you cannot make a distinction. Nobody wins. So you don't have EZ. So therefore, that would be 1,1,2-trichloroprop-1-ene. Okay, obviously, you pick the one with the 2 chlorines and the double bond to be carbon number 1. So it's 1,1,2. Does that make sense, everyone? So not every double bond has EZ. It could be the case that it just doesn't matter because it's the same. But a lot of times it will matter. And a common mistake is you forgot the EZ on the test. Please don't forget the isomerism of double bonds. So no more questions? Shall we move on?
Yep.
All right. What about this page? None of them are the same. The first one. You have all the halogens here. Is that E or Z?
Wait.
Like,
So
I
that-
feel,
Say what?
I don't know.
I mean, if they're all different, how do you do this? Eric, you have an idea?
Did you do the atomic number?
Yeah, you just compare the atomic number, just like before.
Bromine and iodine? Or
Yeah, they will be the winners. Bromine, I think it's 35 compared to 17 for chlorine, so bromine's the winner. Iodine, I think it's 79. I could be wrong, but it's lower on the periodic table, so it must have a higher atomic number. That's got to be higher than fluorine, and that's the winner. So the 2 winners are on the same side. That would be Z. Okay, and there are 2 carbons here. Which one is carbon 1?
the right? No.
The one on the right.
Wait. Is it on the right?
The one on the right. Why?
Do you do the sum of the atomic number?
No. No, we're talking about numbering carbons.
Yeah.
Atomic number has nothing to do with the numbering of carbons. Remember? But what
Do you
does?
do it alphabetically now?
Yes, alphabetically. Okay?
To the left side?
So, yeah, the one on the left is carbon 1. Now, the first thing you look at is the double bond. Which direction gives me a smaller number for the double bond? It's 1, 2 in both directions, so that doesn't matter. So that's a tie. So which one give me the smallest set of numbers? You're going to get a 1, 1, 2, 2 regardless of which direction. So again, that's a tie. So only then do you go to alphabetical order. Bromine B, you're the winner because you're the second letter in the alphabet. So you're carbon 1. So you have, first for bromine and iodine on the winners. 1 Z, 1 bromo, 1 chloro, 2 fluoro, 2 iodo, ethene. You good?
Yep.
I wrote ethene, not eth1-ene.
Oh,
You don't need the 1-ene. because if you're ethene, you've got 2 carbons, well, of course the double bond is between the 2 carbons. There's no need to specify it's on carbon 1. It's got to be on carbon 1. Okay, does that make sense?
Yeah.
So let's move on to the next one. Between the Cl and the C, well, the Cl is the clear winner here. And on the right side, between the bromine and the iodine, because iodine is lower on the periodic table, iodine is the winner. So now they're on opposite sides. That therefore would be E. Okay, and you have 3 carbons this time, and it's a no-brainer which one is carbon 1, the one with double bond and the 2 halogens. So that would be 1 E, 1 bromo, 2 chloro, 1 iodo, prop 1 ene. Okay, do we have any issues with this one? And we learn new rules, but don't forget old ones. Okay, 1 bromo, 2 chloro, and then 1 iodo because of alphabetical order, B, C, and then I. Okay, and the last one, the 2 chlorines are on opposite sides. So this one is E or Z.
Z.
Z means the same side. If you say Z, you'd be right. That's a trap. Okay. If you just look at this, you'd be like, hey, I have chlorines on opposite sides, so they must be trans. So opposite, I'm going with E. No, it's Z. Because B has a higher priority than, bromine has a higher priority than chlorine. And then on the other carbon, chlorine has a higher priority than fluorine. So the high priority groups are on the same side. You don't care what they are. You don't care that there are 2 chlorines. You just care about who has a higher priority. And that would be a Z. It's the same side. So it's 1 bromo, 1 2-dichloro, 2 fluoroethene. Are you guys good?
I have a question for the one at the middle one. Like when we named it, we said like 1 iodoprop and then 1 ene, but the other one's like ethene, like.
Why is there a 1 in the second one?
Yeah, like, yeah.
Technically, you don't need the 1 for the propene.
Mm-hmm.
Right? But think about it, right? Because that can never be on carbon 2. Because if it's on carbon 2, we're not following the rule. We're not numbering it correctly. Mm-hmm. Technically. Because we didn't learn the situation where it can be on carbon 2 yet.
Okay.
So right now, double bond is the boss. So it has to be on the smallest number. That's not going to be true on Tuesday. If the question says 3E, you better have the higher priority groups on opposite sides. And that takes some planning ahead. You can't just close your eyes and start drawing, because if you do, you might screw up. And in the end, you'll be like, oh, crap, I drew everything correctly except the cis trans. So I'm going to have to erase that and do that again. So when you draw alkenes, I highly recommend that you draw the double bond first. After you draw the double bond, you draw the cis and trans, and then you fill out the rest of it from there. So that's to avoid having to go back and erase everything. All right, so take some time, draw these 2 compounds, and I'll take them up in around 2 to 3 minutes. Keep in mind your drawing doesn't have to match mine. What I mean is yours could be rotated. It could be flipped. Okay, as long as it's structurally correct, it's fine. But the structure must be the same as mine. It's just the orientation might not be. All right, I'll give you 2 to 3 minutes. All right, so here's what I have. I kind of cheated. I used a computer to draw this. On paper, I would draw something similar. I have the double bond on carbon 3. Okay, and there are 7 carbons in the longest chain, so hep 3-ene. And I made sure that it was an E orientation. So they're on opposite sides, the high priority groups. So then the 4 and the 5, they both have a methyl. And on the and on carbon 1, you have a bromo and a chloro. And this has to be E. So if I draw the bromo on top, then the rest of the molecule must point down because they must be on opposite sides. Okay, again, yours could be flipped. Your reactions of alkenes. With reactions, first of all, you have to realize what functional groups are. We're going to be learning about functional groups from this point onwards. And a functional group basically is a group of atoms that changes the property of a molecule. It gives it more interesting properties. Alkanes are really boring. They're really mundane. They're unreactive. They don't really do much except burn. So if you change that structure, you give it like a special atom, like here, have an oxygen or have a double bond, then that would define the property of the substance. It will become more reactive. Okay? And double bonds or triple bonds, they are considered to be functional groups because they change the property of the molecule once you get one. Okay? And they will react more easily. And one of the most common reactions of alkenes and alkynes would be addition reactions. Okay, and addition reactions are different from substitution, the one we learned yesterday. Substitution, you switch. Okay, I give you one, you give me one. Addition is you basically take two things, you combine them into one bigger thing. That's it, you have one product. Okay, so hence addition. So there are many kinds of addition reactions with alkenes. Starting with hydrogenation, if you just add hydrogen to an alkene, what happens is after you apply catalyst, heat, and pressure, you will break that double bond, and instead you will saturate your alkene to become an alkane. Right, so that's why you have addition. That's it. That's very clean. That's the only product you have, just an alkane. If you add a halogen, like bromine or chlorine, to an alkene, same thing. All right, they will break the double bond, and you will saturate your alkene to become an alkane, but it will be an alkyl halide with halogens on it. Does that make sense? Two things becoming one. You don't need to get anything back because once you break that double bond, it is missing two atoms. Just provide the two atoms and you're good to go. You don't need to switch. And another type would be hydration. You add water to an alkene. And if you add water, if you think about it, water is just H bonded to a hydroxide, OH. And if you add a catalyst to that, well, the water will break into H and OH, and one carbon with the double bond, well, single now, will get the H, and the other carbon will get the OH. Okay, and you will form an alcohol. Don't worry about the name of that alcohol. We will learn how to name alcohols in another lesson. When we do learn how to name alcohol, it won't be that name. Okay, that name is an old name. We have a better system now. The last one is hydrohalogenation. So you have hydrogen bonded to a halogen, so hydrogen halide. You can also mix this with an alkene. And when you do, the hydrogen will break off the halogen, and across the double bond, one carbon gets the H, one carbon gets the halogen. Okay, so in the hydrohalogenation reaction, you can see that you can have one of two products. The hydrogen can go on the first carbon, or the hydrogen can go on the second carbon. Which one is it? Is it 2 bromopropane or 1 bromopropane? Does it matter which one it is? The answer is yes. Okay, we do know which product is produced. Actually, both products are produced, but one product is preferred over the other. So you have more of that product. Which one is that? According to the Markovnikov rule, whichever carbon has more hydrogen, they will get more hydrogen. Whichever carbon has fewer hydrogen, they will get the halogen instead of the hydrogen. Okay, that's Markovnikov's rule. In one short phrase, the rich gets richer. If you're already rich and swimming in hydrogen, you'll get more hydrogen. Okay, if you're flat broke and have very little hydrogen, well, you're not getting more hydrogen. It's kind of like real life. Okay, if you're already rich, it's really easy for you to make money. If you're broke, it's actually harder for you to make money because you need something to start a business. You got to have some kind of cash flow. But if you're swimming in money, like Bill Gates doesn't have to do anything anymore, just put that in the bank, the interest will be many times my salary. Okay, so life is not fair. If you ever play the game Monopoly, it's a very, very agonizing game. I get pissed every time I play that game. If you're doing well, the money rolls in. If you're poor, it becomes worse. Okay, basically this is Markovnikov's rule right here. So according to this rule, if you look at the propene, across the double bond, one carbon has two hydrogens. The other carbon has just one hydrogen. Well, the rich gets richer, so the carbon with two hydrogens will get the last one. That will become three hydrogens. And the carbon with just one hydrogen, you're getting the bromine. So 2-bromopropane is the preferred product. Okay, we call this a major product because you mostly make this, but you still make the other, just in lower proportions. Okay, do we have any questions regarding Markovnikov's rule? All right, cool. So questions like this will be expected of you. I will give you a reaction. I will describe the reaction in words, and you have to draw them. So what compound will be produced when water reacts with 3-ethyl-hex-1-ene? Okay, first of all, you got to draw the compound. And then once you draw the compound, you have to figure out, okay, so what will this make with water? And then draw the product. Does that make sense? So attempt this question. I'll give you around 2 minutes, and then I'll take this up. Alrighty, so you have to draw the compound first. 3-ethyl-hex-1-ene, it looks like that. Now, keep in mind that in this one, I drew all the carbons and hydrogens because I wanted to show the Markovnikov rule. Okay, you don't have to have the carbons and the hydrogen. You could just draw the skeleton, but no, for the sake of learning, I included the hydrogens. So this is it. You need to add water to this. So water must be added across the double bond. Somebody gets the H, somebody gets the OH. Okay, who gets the H? Well, Markovnikov. Rich gets richer. So the carbon already having two hydrogens will get the last hydrogen. So this one right here. Okay, let me just highlight that one for you. So there's your hydrogen. And the other carbon, deficient of hydrogen, will get the hydroxide. And this will be your final product. Did you all get that? Something similar? All right, so this will be the last little bit. And oh yeah, you have to name them. But again, we're not learning how to name alcohols yet. And even if we do learn how to name alcohols, this wouldn't be the name that we're learning. That will be the name. 3-ethyl-hexane-2-ol. That will be the proper name of this alcohol, which we will talk about in 2 classes from now. Okay, but on the test, you would have learned how to name alcohol, so you would be expected to name something like this. So do we have any questions before we finish? This is it. We learned about alkenes, what alkenes are, how do they react, how do you name them, cis versus trans, Markovnikov's rule. Okay. Any questions so far? No? All right then. If this is the end here, I'm going to pause and stop the video.